SwayamPrabha. Digital India. Educated India.
Welcome to week 9 of the NPTEL course on Muffler Acoustics. So, as promised at the end of the last lecture, that is lecture 5 of week 8, in this week we will be primarily focusing on cross flow elements. So, let us try to understand what a cross flow element is, and before moving on to more complicated things like multiply connected mufflers. So, we in the last class we saw, before we actually talk about cross flow things, let us go in a very systematic manner and try to draw this thing. Okay. So, this was a ECTR. Okay. So, extended concentric tube resonator with extensions at 1 and 2, okay, something like this. Now, suppose we have this element and then the flow really just sort of grazes the boundaries. Okay. The flow just grazes the boundary. The flow is not allowed to go through the element. Basically, the only way the flow can go through the pipe. So, here the only thing that is important is the grazing flow impedance. So, here only the Mach number mmg, the grazing Mach number is important, mb or the bias flow Mach number is 0. So, what is bias flow? So, bias flow is when the flow has to necessarily go out of this and there is another duct and the flow again enters the another duct, which I will draw soon, and then it goes through this thing. So, basically the flow, the velocity that goes through the ducts, if that is non-zero, then you have a non-zero bias flow or you have a cross flow element. So, let us then get to the cross flow elements. So, let us see how they look like. First of all, they must have at least a 3 duct interacting system. All this while, like in this figure, we have a 2 duct system, okay, because this is the first one, this is the second duct. Okay. Now, if we have a 3 duct system, something like this, okay, something like this. So, let us see how we go. So, this is your first duct, this is your second duct, and this is your third duct. That is the duct or the main chamber that houses both the pipes. Okay. So, this is a common section that you are seeing from here and from here, okay, something like this. So, basically how does the flow interact and what sort of element can we form. So, we can sort of draw the configurations. Suppose we have this kind of a thing, okay, the flow comes in here and it can be a circular section and you have a perforated section. So, you have this. So, you have this kind of a thing. So, and it goes like this. Okay. The flow has to necessarily come out here and again graze and become like a grazing flow in the duct 2. So, we can name this duct 1 inlet, you can name this as duct 2 outlet, and duct 3 which is the chamber itself. Okay. So, these are all perforated sections, and notice this is an overlapping perforated section. It need not be always, but for simplicity we are assuming, and there is one wrong thing that I did here, we should be a cavity like this. So, this is called a cross flow expansion chamber, because the flow really has to expand and it is like a straight through kind of a configuration, not exactly a straight through, because the flow comes like this and it kind of it has to, we have to understand the difference between this configuration and this one. So, the flow need not go out, or the mean flow itself need not go out of the perforates in the ECTR case, but in this there is no other way that the mean flow can leave the chamber cleanly. Okay. The flow has to, whatever, if q naught is the flow velocity here, and if Sp is the cross section area, so clearly q by Sp is the velocity u naught in the pipe. Now a simplified hypothesis, obviously this needs to be a proper way of dealing with evaluating the mean flow distribution would be either through lumped resistance analysis, which is given in some recent papers, or maybe if one wants to do it very properly, then CFD analysis would be even better, because these flow distributions would be rather non-uniform, given the fact that the flow has to come out of the perforates. Again there will be some non-zero velocity, radial velocity like in this direction, and okay, and then it has to again enter and go. So basically the idea is that this q naught is split into two parts. One is going through the grazing or the axial direction, and it gradually reduces. For simplicity you can assume a uniform grazing flow in the pipe 1, and then it comes out and sort of reattaches again. So basically your velocity q naught here, it's you can equate this to the area of the perforates. So what is the area of the perforates? Sigma into pi d, let us say d is the, or dp is the diameter, dp into lp, lp is the length, lp is your this length. So this is your area, curved area, into the porosity, that will give you the effective area of the or the net area of the total number of holes. So sigma into this, into, if you multiply this entire thing by u dash, so this if we equate to, say, we know u naught, we know Sp diameter, so one can figure out easily the u dash, or the velocity u dash is really in this direction, that is the velocity coming out through each of the holes. Again this u dash will tend to be more to as the flow goes along this direction for this configuration, and it will tend, as we approach this hole, it will tend to be 0, and finally you have a grazing flow tends to really be significantly different from non-zero, that is this value approaches this value more towards this direction. Again there will be some losses, so whatever u naught we are seeing here, that will not really be the case here. There will be, you will get a slightly lesser velocity here because of losses. That is what happens in a real world. But nevertheless, as a very gross or a first approximation, I guess it will be a decent approximation if we were to do something like this, where this is LP and this is sigma. So we can write u dash as u naught into pi d square by 4 into pi d this dp LP. So this goes, this is like this, u naught by dp into 4 LP up. This is just an approximate value of the grazing thing. So if you have this m dash, this is m naught, the grazing one, into dp by 4 LP. So generally your diameter of the pipe is pretty small, about 40 mm, 50 mm for automotive mufflers, and LP is your length of the perforated pipe, which is usually more than the diameter. So again this quantity, and plus it is divided by 4. So this and Mach number, again it is about, this maximum value is about 0.15 or something like that. The point is that the bias Mach number will be even smaller. So, and mind you, these kind of configurations, that this is called a cross flow expansion chamber, okay, cross flow expansion chamber. So and yet you have another such simple configuration which is called a reversal flow, or something like this, something like this. So the flow again has to enter here, go like this, come out and reattach itself. So this is called a cross flow reversal a reversal chamber. So, here also the flow has no other option but to navigate through these perforated holes and come out of this. So, this can be your inlet, this can be your outlet, and this is the chamber itself. So there is only one way the flow can go. Now, I know this is a topic for a little later, but typically what one can also do is that one can, suppose if we were to have such a kind of a thing, this kind of a thing. So, then the flow has multiple paths really. So, this can be your, you can have a flow like this, and then you can also, the flow can actually take a complete U-turn smoothly, and then it can go through like this. So, these such configurations, and these are called your short end chambers. Remember, we were discussing about wave propagation along the transverse direction. So, this can be of elliptical shape or circular shape. I am not drawing here because of lack of space. Similarly, you can also have something like a resonator here, and things like this. Waves can also go like this, but again there will be a unique path, or you can also sort of get things like this thing here, or maybe just a port. I am sorry, you can just have a port like this. So, we can have multiple such things. So, then you will have really multiple ways in which the waves can go. I am sorry for that. So, be like this. So, you can have a port here, and you can have multiple ways in which the waves can go. The waves can go like this and it come out like this, or maybe it can directly go through this. So, there will be the flow might just have one path, but the waves can definitely take non-unique path. In this case, the waves can go like this, or it can go like this, and number of things it can do. So, such elements are called multiply connected elements. This is just one sort of very simple sort of example. There are much more complicated examples of multiply connected mufflers. So, then of course, talking about such configurations, there are many more such configurations what one can probably deal with. Another configuration that we sort of have is your extended non-overlapping perforated thing. So, this can be something like this. You have a pipe like this, and there are non-uniform things like this, and you have perforates all across like this, and you have things like this kind of a thing and this. So, the flow comes here, it has to go through this, and finally leaves. Okay. So, here the flow can of course expand and again do like this kind of a thing, and you can also have things with an overlapping section. So, in such a case you can have this kind of a thing. So, these are called your open-ended perforated elements, because flow is just allowed to expand. So, here there is no guiding thing, such things are not there. Okay. The little bit drawback about this configuration is that it has a back pressure or head loss, because the flow is just allowed to expand, and who knows, it might be much more counterproductive compared to the case where you have this thing where the flow is easily guided. At least the flow cannot go through, there has to be resonances that are developed in this part. So, there are pros and cons for each of the muffler configuration depending upon your flow velocity and your thing that you want to analyze. You can have different sort of configurations. So, now I guess with this bit of understanding, what one can do, and mind you, these are all of uniform cross section area. So, the area of the circle or the ellipse does not really sort of change. Now, what one can really do is basically develop or set up the system of equations that are really necessary to go ahead with our analysis. So, what we will do, we will revert back to our configuration. I will sort of just rub this, or probably I will draw this again. Anyways, I have to talk about this configuration. So, basically let me just write down the equations for this duct with the understanding that we still use a control volume approach. we have to take a control volume here, find out the fluxes that enter inside, go outside, and then the ones that go here, and equate them to the temporal rate of change. So, then you have momentum equation here, you have your momentum equation here, continuity here, momentum here, continuity here by using a control volume approach. So, this is going to be a little bit algebraically tedious, but hopefully when we do a systematic job we can overcome all the challenges associated with it. So, let me just write down, that was slide number 17. So, I will go to slide number 23 and start writing down the equations for different ducts. So, you have this, and and then you have this kind of a thing. So, I will number the duct 1 section 3, this duct as 2. Okay. So, the continuity equation for duct 1. So, we have rho naught into del u1 by del z plus u1 is the velocity, let us say, that goes here, and your del rho 1 by del z, okay, plus 4 times d1 into rho naught u1 comma 2. So, I will tell you what do I mean by this guy, minus del rho 1 del t. So, u1 comma 2, this is nothing but the difference in the pressure P1 minus P2 divided by rho naught C naught into xi 1. I would say, I would just assume equal perforate impedance, that is what the case is in most of the commercial mufflers. So, it is fairly general to keep it xi and not xi 1, it will not make much of a difference. So, and then you have your momentum equation for the duct 1. So, this is your u1. So, I am dropping off all the tilde signs. So, apologies for the any confusion. So, this is your, let us say this is capital U1 naught, I would say, or just U1 capital U1 is equal to minus del P1 by del Z. So, this is your momentum equation. Okay. This is a momentum equation for the inner duct 1, and for the duct 2, that is your I mean the main duct or the chamber that houses both the things. So, for such a thing is your you have U2 and del rho t by del z minus 4 d1 by d2 square minus d1 square minus d3 square, because this is really your annular area, into rho u naught 1 comma 2, where u1 comma 2 is something that we have just seen, and plus 4 d3, because see in this configuration whatever comes out, it also sort of enters here. So, when we do I am just leaving out the details because we have a fair bit of ground to cover. So, I am just simply writing out down these equations. So, u1 comma 3. So, I will tell you what this thing means. So, this is something like your u2 comma 3 is nothing but P2 minus P3 divided by rho naught C naught xi. So, this is what it is, okay, and this we have already seen. So, we have this thing, and then you have your momentum equation in this duct, which is of course your del u2 by del t plus u2 is velocity. So, maybe it is good idea to introduce those tildes just to sort of prevent any confusion. So, I just have to go back and keep doing this tilde business. Okay. This is like this. So, now things should be more clear. This is like this, and okay, and rho into del u3 by del z u3 t. So, we get this sort of a thing, okay. And here you have your rho naught into d dt of u3 tilde, and so this is your momentum in the second duct, and this is your continuity equation in the third duct, and this is your u3 tilde, and this is your z, okay, in the third duct. So, we have this sort of a thing. Now, you know, really we have how many? 6 equations, actually more, because let us start numbering them. 1, I would say, you know, 2, because we need that many relations. So, 2, 3, 4, 5, 6, 7 and 8. So, you know, u23 and u13, that can be simply be replaced by putting in appropriate expressions like, you know, 5 and your 2, okay. So, your equations that were numbered like until I guess 8, that gets reduced to 6, okay. So, when we have such a thing, we have you know we get 6 equations, and the number of variables that we have, how many variables do we have? We have p1 rho 1 u1 tilde, I am sorry, p1 tilde u1 tilde rho 1 tilde here, and you have your such things for the second duct and your third duct. So, basically 9 variables. Now, we have only 6 equations. So, then what we do is that we use isentropicity relation. So, that is, you know, now it is should be fairly simple or straightforward for you guys to notice to make use of such expressions, and have this. So, you have additional 3 equations, 9 equations, 9 variables. I would say, you know, substitute all these guys into the respective places wherever they occur. So, as a result, you have your variables down to 6, and you have 6 equations, namely your p1 tilde, u1 tilde, p2 tilde, u2 tilde, p3 tilde and u3 tilde. So, you have 6 equations and it becomes algebraically very messy. So, I hope to share with you the only the you know the way it is finally written in a maybe in a new slide, but this time around in this particular fashion or this kind of a thing. So, now notice rho naught C naught u1 tilde has the same dimensions as p1, and that is why, you know, choosing this will eliminate any ill conditioning problems in MATLAB, because anyways you are going to use the exponential function to sort of integrate. So, you know, you have your dash. What does dash means? Dash means ddz, spatial derivative with respect to the axis. So, this was your, mind you, this was your axis z, isn't it? So, you have your derivative and this. So, I will sort of just rub this guy, and with the understanding that you have a derivative sitting here, and this is your gigantic equation. So, you have your p1 tilde, p2 tilde, p3 tilde, rho naught C naught u1, rho naught C naught u2, rho naught C naught u3, and you have your this 4 5, and then you keep getting these equations, okay. Then we can just write it down: a11, a12, a16, a26, a36, a66. So, a21, a31, a61, a62, a65 and so on. So, you know, one can sort of populate the entire thing, not an issue. So, we can do that, and again the procedure then is rather straightforward. You know, you basically, so let us say we have this big variable. So, at section z is equal to 0, we equate by exponential exp m, and I would call this as A matrix over the length L times this entire thing. So, this is the road map at z is equal to L, that is what we sort of get. So, it is a big matrix, namely 6 cross 6 matrix as compared to 4 cross 4 matrix, because it is a fully coupled thing. Okay. And now what happens is that couple of things that I want to mention here. First of all, if you have these equations are already looking very nasty, these equations are looking really sort of a bit difficult to handle, in the sense of doing this hand calculation. So, the hand calculations are anyways ruled out, you have to use a program, some MATLAB, Fortran and all that things. In MATLAB life is a bit easier, like I said. Now, what we have to do here is that a further simplification can possibly be done by understanding that going back to these equations, possibly noticing these things. I was talking about Mach number being very small. If it is 0.15 in the main duct where the flow enters, so it is going to be even smaller in the annular cavity, and the bias flow is going to be even smaller. The point I am trying to make is that the convective effects of mean flow in the duct as well as in the chamber, that is duct 1, duct 3 and the overall chamber duct 2, can be simply be ignored while retaining the dissipative effect of the perforates in the perforate impedance expression. So, because that is what matters the most, even if you were to ignore the convective effects and just retain the dissipative effects, it would be okay to get at least some kind of a decent approximation, because you remember perforate impedance tends to have a non-zero real part or resistive parts when the flow is there. We saw from the expression given in LRD's paper that we have been using in MATLAB codes. So, it is a pretty involved expression, and you have to take the real part and imaginary part and all that. So, the point is that the mean flow definitely has adds to the real part, as we can sort of I can pull out that equation. This was the one. Okay. So, so this was the MATLAB script, MATLAB code. So, this is the real part, and you see mean flow is there. So, it definitely does contribute to the resistive losses or dissipative losses in the mean flow thing. So, especially when the point is that if you include these non-zero mean flow in this expression and sort of ignore or purposely do not consider these U3, big U3 or U2 for that matter, U3 or U1, you will be still better off. You can simplify things and yet retain the most important effects. So, what we will do in the next class, that is tomorrow's class, lecture 2 I mean, is that we will set up these equations with a little bit of simplifications and do some MATLAB coding and do some MATLAB demonstration on for simple configurations and try to evaluate the transmission loss, at least for the case of non-zero for the case of zero mean flow by assuming suitable expressions, perforate impedance expression, and possibly doing some calculations for non-zero mean flow, non-zero grazing and bias flow in the pipes. So, we will do all those things, and hopefully that should set us up for advanced configurations in this week and possibly in the next one. So, till that time, thanks a lot, and I will see you tomorrow.